Welcome to Manifested Publishers.
Welcome learners, my name is Stephen Kariungi. Today we continue with our chemistry topic, the structure of the atom and the periodic table. And today I would like us to discuss relative atomic mass. So relative atomic mass is the average mass. And this average mass of an atom is compared to the mass of carbon-12, whereby carbon-12 is assigned an atomic mass of 12. So we are saying that relative atomic mass, this is the average mass of an atom of a given element compared with one atom of carbon-12 whose mass is 12.00. So that is the relative atomic mass. There is a formula that is used to calculate the average mass or the relative atomic mass, especially where we have isotopes. We know that isotopes are atoms of the same element having the same atomic number but different mass number. So if you have different mass numbers of the same element, then we can be able to calculate the relative atomic mass or the average atomic mass. Before we do that, it's also important to say that a relative atomic mass is measured using an instrument called mass spectrometer. So let's look at determination of relative atomic mass, which we shall abbreviate as RAM. So the formula for calculating RAM is equals to the mass of isotope 1 times its percentage abundance plus the mass of isotope 2 times its percentage abundance. That is, if we only have two isotopes. But if the isotopes are more, then you can go to plus the mass of isotope 3 times its percentage abundance. Let's take an example. That an atom of chlorine has a mass of 35 and a percentage abundance of 75%. Another atom or another chlorine atom has a mass of 37 and a percentage abundance of 25%. So we are given an example there whereby we are required to use the formula that is given. An atom of chlorine has a mass of 35. That is the mass of one atom. The percentage abundance is 75%. That is the mass of isotope 1 times the percentage abundance. Another chlorine atom has a mass of 37 and a percentage abundance of 25%. Then you are supposed to use the formula to determine the relative atomic mass. So we'll say that RAM is equals to the mass of isotope 1, which is 35, times its percentage abundance is 75%, 75 over 100, plus the mass of isotope 2 is 37, times the percentage abundance is 25 over 100. So if you say by 25, 1, 4, 4, 1, that is 6, 1.25. Here by 25, 4 by 25, 3, 4, 1, 8, 32, 3, 5. .75. So that is 8. That is 15. 2. 26 plus 27. So 29.25 plus 6.25 is 35.5. So the relative atomic mass for chlorine is 35.5. So that is using the formula that is given there. Can confirm again. The change 26.25. .25. So that comes to 35.5. So basically we are saying that the relative atomic mass is calculated by taking the mass of isotope 1 times the percentage abundance into brackets plus the mass of isotope 2 times the percentage abundance. If there is isotope number 3, you say plus isotope number 3 times the percentage abundance up to all the number of isotopes that are present. Now, the answer that you get should be closer to the mass of the isotope that has the highest percentage abundance. So in this case, the answer that 5.5 is closer to the mass of 35, which has the highest percentage of 75%. So you can say that the RAM should be closer to the mass of the isotope with the higher percentage abundance. So we're going to have an assignment based on this. So the first question in the assignment, an element X consists of 3 isotopes with mass numbers 22, 24, and 25, and percentage abundances of 89.6, 6.4, and 4.0%. Determine the relative atomic mass. So there you'll just apply the formula as it is. In question number 2, an element P has 2 isotopes with the relative percentages of 65 and 35. If the mass number of the 2 isotopes is X and 31 respectively, so that means that the one with a percentage of 65 has a mass of X, so we don't know the mass, and the one that has a percentage of 35 has a mass of 31. Find the mass number represented by X given that the RAM is 30. So in this case, you're supposed to calculate with X as the unknown. But on this, we know the relative atomic mass. So we can be able to work backwards, still using the same formula, and get the mass of isotope that is X. So we'll stop there. Until next time, goodbye.